Hi everyone, thank you for joining. Today I will be presenting an AI-driven flood inventory generation from multi-source remote sensing to reliable flood susceptibility mapping. This work focuses on how we can leverage artificial intelligence and remote sensing data such as optical, radar, and topographic information to automatically generate flood inventories and improve susceptibility mapping. By the end of this presentation, I hope to show you how AI can transfer traditional flood susceptibility mapping into a more automated, scalable, and reliable process for disaster risk management. Floods are among the most frequent and disturbing natural hazards globally. Their occurrence is increasing in both frequency and intensity, driven by climate change, rapid urbanization, and land use change. Economically, flood costs billions of dollars in damage every year, destroying infrastructure, farmland, and housing. Beyond the financial losses, they bring widespread human suffering from large-scale displacement to tragic loss of life. For example, the catastrophic flood in Iran in 2019 caused more than 4.1 billion in damages, affected 20 provinces, especially Golestan and Khuzestan, and led to over 77 deaths. According to European Commission's Flood Risk Index reported in March 2025, countries such as Bangladesh, Egypt, and Vietnam have the highest risk score globally, and reflecting their extreme exposure to river floods. Thailand also followed closely with a score 9.8. To effectively respond to the challenges posed by floods, we need more than just event-based flood maps. This is where flood susceptibility mapping plays a crucial role. Susceptibility mapping is the process of identifying areas most likely to be flooded in the future based on the multiple factors such as historical flood records, rainfall, river proximity, topography, soil condition, land use, and etc. The result is a probability-based map that classifies regions in high, medium, or low susceptibility. Unlike hazard maps, which focus on individual events, susceptibility maps give us a long-term view of vulnerability. These maps are vital for urban planning, emergency preparation, infrastructure protection, and insurance assessment. But most importantly, they help save lives by reducing disaster risk. As shown in the workflow diagram, susceptibility mapping typically requires two main inputs. For example, flood conditioning factors such as rainfall, slope, dam, land use, land cover, and soil properties, and etc. And a flood inventory map that provides ground truths of flooded and non-flooded points that can be used for the modeling step, which can be based on the AI, machine learning, hybrid approaches, or statistical methods. The model then produces a prediction map across the entire study area, classify it into different levels of susceptibility from low to high. This process gives us a far more reliable and forward-looking tool for managing flood risk. At the heart of flood susceptibility mapping lies the flood inventory. A flood inventory is essentially a collection of flood and non-flood points. Each point tells us whether a location was inundated or not during past flood events. These inventories act as the ground truths that our model learned from. Their role is critical. They define the known reality against which models are trained and validated. Without accurate inventory, susceptibility maps can become misleading, which is dangerous for planning and disaster response. Most research has historically relied on traditional methods to build inventory, like sparse ground observation, manual interpretation of the satellite and aerial images, and delayed post-disaster surveying. While this approach provides useful information, they are slow, costly, and incomplete. And the climate change also changed the pattern of the flood, and we need to update the flood inventory. This is why improving inventory generation is such a key research challenge. It's not just about mapping flood weather. It's about building a reliable data set that drive our susceptibility models. So compared to the traditional methods, remote sensing-based flood inventory mapping give us well-distributed flooded and non-flooded points across large areas. Satellites such as Sentinel-1 and 2, the Landsat series and Madison, etc., provide free access, frequent revisit time, and different spatial resolution, which together make rapid large-scale flood analysis possible. Much of this processing today is carried out on Google Earth Engine, a cloud-based platform that let us analyze dedicated of the satellite archive without the need for local high-performance computing. The diagram here summarizes the general workflow for generating a flood inventory. We begin with multi-source remote sensing data, for example, Sentinel-1, 2, Landsat, and MADIS, each contributing different strengths for flood detection. The first step is pre-processing, like, for example, atmospheric correction for optical imagery and spectral filtering for SAR images. Next, we carry out bitemporal or multi-temporal analysis to extract the feature like NDWI from optical dataset or backscatter differences from the bitemporal SAR images. Flood detection then follow often using thresholding method like ADSO in traditional workflow. These produce binary flood maps, and when multiple events are analyzed, they can be aggregated into a flood frequency map. From this map, we then sample flood and non-flood points, which form the flood inventory database used for susceptibility modeling. It's also worth noting that this workflow can be applied to individual sensors, like, for example, Sentinel-1 alone, or a multi-sensor combination, for example, pairing Sentinel-1 and Sentinel-2 or Landsat or MADIS. Depending on data availability, this can present the same event or different flood events over the time. So let's briefly look at the traditional port processing method like ADSO thresholding. It's an intensity-based classification that analyzes the histogram of pixel value and finds a global threshold to separate water from the non-water. In flood mapping, it's applied to indices like, for example, DWI or MNDWI from optical images, or in the Sentinel-1 SAR backscatter. Also, is widely used for large area rapid flood detection, which can be easily programmed in the cloud-based platform like Google Earth Engine. The result of this thresholding is a simple binary flood maps and can show us the flooded and non-flooded area, which is then turned into a flood inventory. And the flowcharts show a practical workflow for ADSO-based flood inventory generation using Sentinel-1 SAR data. First, the SAR images undergo a formatted processing, like, for example, noise removal, calibration, training correction, to prepare them for analysis. Then throughout spatial, temporal, and spectral filtering, pre- and post-flood images are cleaned and aligned, and the workflow continues with automated change detection, where permanent water and steep slopes are masked to avoid false detection in the final result. At the core of the method, also thresholding is applied to the SAR backscatter to separate flood and non-flood pixels. They are merged into flood extent maps from which flood and non-flood are sampled to create a flood inventory. Finally, the inventory is validated against both field survey and the global flood database, ensuring accuracy. For example, this is the first example comes from Ahvaz city in Iran, where the ADSO-based method that I previously explained, this was used to generate the flood inventory. This is the first try in generating the flood inventory based on the remote sensing images. And in this model, the Sentinel-1 SAR images from a single large flood event comparing pre- and post-flood images was proceed in Google Earth Engine, and also thresholding was applied to extract flooded area. These were then sampled into flood and non-flood points, and this point along with conditioning factors such as soil length, cover rainfall, and topography, and etc., were used to train support vector regression model for the optimized by meta-heuristic algorithms like IDWO. and FR, and so on. And this model produces reasonable susceptibility maps, which AOC value between 77 and 81%, and the hybrid model performed better than standard Southern vector mesh. However, the flood inventory relied only on one major event from pre-10 cross-Sahara images, which does not capture the broader historical context of the flooded and non-flooded area, even though sparse historical flood points were added in this study. In the second example, our colleague Chiranjit Singha worked on the one area in the eastern of India, using a more extensive data set from Sentinel-1 Sahara images from 2020 up to 2023. And they used the same approach, like also thresholding to separate the water and non-water area, and then they generated the flood inventory from the frequency map. And as shown, most flooded points were sampled from the zone with higher frequency of inundation. This point, combined with hydrological and topographic factors, were used to train the cellular machine learning model, including random forest gradient boosting machines, upper vector machine, and artificial intelligence, with the analytical hierarchical process like AHP for weighting. The reported results were strong, with AOC value around 90%, indicating high predictive accuracy. However, the reliability of this workflow still depends heavily on auto-thresholding. In case where floods are smaller or less distinct in star images, this thresholding step can introduce error, limiting the overall robustness of the inventory. So both auto-based and traditional machine learning models have clear limitations. Also rely on a single threshold, which only works well when there is a sharp contrast between flooded and non-flooded pixels is clear. In real conditions, with star noise, vegetation, or mixed boundaries, it often misclassifies and generates misleading inventory. A traditional ML or machine learning model like random forest and support vector are more flexible, but they still depend on manual training data and feature selection, and often need to retrain for other regions. This is why we turn to AI-driven methods, and the AI-driven method can integrate multi-source data, learn complex non-linear patterns, and generate more reliable, scalable flood inventory. While AI does need a large data set, these challenges are being addressed with new and available benchmark data sets, such as, for example, SEN1 flood 11 for SAR images, or WARD floods for optical images, and multimodal data set like, for example, MM flood that also include DEM and auxiliary variable beside of the Sentinel-1 and Sentinel-2 images. So the workflow for AI-driven flood inventory generation is similar to the traditional one, but with a major differences. Instead of using simple thresholding, the flood segmentation step is handled by deep learning models, which greatly improve the reliability, accuracy, and generality. Here, for example, we show an encoder-decoder architecture. Top many model types can be applied. Assuming these models are already trained on the benchmark dataset, we can design different scenarios depending on the input data. With a single source approach, either SAR or optical data can be processed separately, patched into the model, and predicted, and then assembled into a flood map. With a dual source approach, SAR and optical data can either be processed in a separate models and combined later, or integrated within a dual stream architecture that use both data types in a single model. Once flood maps are generated for different events, they are aggregated into a flood frequency map, which can then be sampled to produce a refined flood inventory. This is another example of AI-driven method for flood inventory generation that currently we are working on it, where the workflow takes advantage of many multi-source datasets to build a comprehensive flood frequency map and form that a flood inventory. And from that flood inventory, in addition to multi-temporal SAR and optical satellite data, we can also integrate volunteer geographic information or VGI images. For example, the citizen contributed images from platforms like CoastSnap, which is very useful for the coastal flooding, while Cloudwater and RiverSnap support river flood monitoring. We can use them. We can also use a global dataset already available in Google Earth engines, such as Global Flood Dataset and Flood Hazard Maps, version 1 and 2. By combining this source, AI model can generate richer and more reliable flood inventory covering a wide range of flood heights and scales. For example, in our recent paper published in Journal of Environment Management, our main novelty was in the area of AI-driven flood inventory formation for flood susceptibility in Mahananda River Basin in India. In this study, we use a deep learning segmentation model to generate flood maps from multi-temporal Sentinel-1 SAR images, and these maps were then combined with the global flood dataset to build a more comprehensive flood frequency map. From that, we were able to generate a refined flood inventory that better represents both recent and historical flooding patterns. Here we see the workflow of our AI-driven method for flood inventory mapping. This process begins with data preparation. This includes pre-processing of the Sentinel-1 SAR imaging and importing auxiliary data like digital elevation model and permanent water layer and global flood dataset for a study area. Next, instead of traditional tertiary, we use a deep learning segmentation model. In this case, we use the transfer learning of the unit to detect flooded area from the SAR images time series. This event-based flood maps are then post-processed, removing permanent water and estimate slope before being aggregated in a flood frequency map. Finally, a grid-based sampling approach is applied, generating a refined flood inventory of flooded and non-flooded points. This inventory further used directly in flood susceptibility modeling, which is here fuzzy AHV XGB groups for the study area. In more detail, we use pre-trained unit model initially trained on the ETCI 2021 Sentinel-1 flood dataset, and this model was adapted to the characteristics of the Mahananda River Basin by fine-tuning its final 35 layers using 100 annotated image patch from the new dataset from one of the images of this area. Trained model then applied on 11 Sentinel-1 images from 2020 up to 2022, as can be seen in figure. The experimental result, rather than units and its variants, like attention-based units, VNet, unit plus plus, unit 3 plus, showed us all model generated better result in terms of the quantitative metric like accuracy with lower trainable parameters. In terms of the sampling, which is very important, once the flooded area are detected and refined, they are aggregated across multiple Sentinel-1 acquisition to build a flood frequency map, which represents the proportion of the times each pixel has been flooded. To make this more robust, the frequency map is combined with historical flood records from the global flood dataset, resulting in updated flood frequency map that reflects both recent observation and long-term patterns. The next step is grid-based sampling. A grid is placed over the study area, and for each node, we use a KD3 search to identify the 25 nearest neighbors. Their flood frequency value are averaged and assigned to that node. Based on this average, nodes are classified as a flood if the value is greater than 0.8 and non-flood if less than 0.1 and unassigned otherwise. This process yields a refined flood inventory providing reliable flood and non-flood points that can be directly used for susceptibility modeling. It's important to note that this is just one way of sampling from a flood frequency map, not best choice. More advanced strategies, such as, for example, adaptive or uncertainty-driven sampling, could be explored in the future work. Here is a sample of the result from our paper where we compared our AI-driven flood inventory generation with the traditional odds-based approach used in our earlier study. The findings are clear. When using AI-based inventory, the performance of the susceptibility model improved significantly. Metrics such as AUC, kappa, and overall accuracy all showed significant increasing, demonstrating that a more reliable inventory directly translates into better susceptibility mapping results. In conclusion, the quality of the flood inventory is critical for reliable susceptibility mapping. Traditional methods like ATSO or classical machine learning are limited by the noise, data dependency, and poor transferability. AI-driven approach, on the other hand, allow us to integrate multi-source data and apply deep learning segmentation, leading to more accurate and scalable inventories. As we saw, this directly improves susceptibility model performance. For the future, we need to expand benchmark dataset, strengthen multi-source fusion, including SAR, optical DM, and citizen science data, and move toward near real-time mapping using platforms like Google S Engine. Exploring advanced sampling strike and linking global dataset with local knowledge will make inventory even more robust. Overall, AI-driven methods are a promising paths for improving flood risk management and resilience. Thank you very much. If you have any question, I can let you know if I can, and feel free to contact me based on this email. Thank you very much.